Hello students, in this video we will continue with photoelectric emission. We know that when light of sufficient frequency is incident on a metal, it gives out electrons, and these electrons we call it as photoelectrons. And also we studied more about it, that Einstein's photoelectric effect, where we said that the incident photon energy h nu given by Planck's quantum theory is equal to kinetic energy maximum of the photoelectron plus the work function, that is the minimum energy required to remove an electron from a metal. It's a very simple process where you have a metal and you incident light of sufficient frequency, and the electrons in the outermost shell are ejected out of it, and it possesses energy because kinetic energy, because it is in motion, and there is a minimum energy required to remove the electron, that is W naught, the work function, and all the energy is supplied by the light. That's why it is called photoelectric, electricity, current. Yes. Now what is this loss of photoelectric emission? These concepts are developed after quantum theory in 1901. After Max Planck's discovery of the quantum theory, h nu E is equal to h nu, energy is in terms of packets, quanta, photons, that it is this, from here the development of explanation for photoelectric emission started. But there's something different actually. So what is this photoelectric emission law says? First one, it talks about intensity of light, intensity of the radiation which we are talking about, which is a light. Now you know that intensity of any light is proportional to square of the amplitude. A stands for amplitude. When you take a wave, for example, when you draw the wave pattern, right, and you'll find that this maximum displacement, we call this as amplitude, right? That is from the rest position or from the mean position. Now here it is talking about frequency. Frequency is number of waves per second, okay, and wavelength is the distance between two consecutive crests or consecutive troughs, okay. So this we can define differently. Now what is the connection between velocity and wavelength? So you know that C is equal to nu lambda. We know this also, where C is the velocity of the electromagnetic radiation, and here we are talking about the light. So nu is the frequency and lambda is the wavelength. Now keep all these factors in mind now. First one is talks about intensity of light. Suppose I take a photo tube. It's very important that we go back to the origin of the photoelectric effect to understand these laws. I told you in the photo tube there are two electrodes, okay. We called it as P and another one as Q, right? This is Q. Now connect this. This is to negative, and this is to positive, negative and positive. Yes, and this is the circuit I have taken. And here we are going to have a key, and I told you this key is going to be a complex key which I am not concerned at this point of time. You see that the electrode Q is basically positive, and I make it less positive and make it negative, and see the effect of electrons ejected from the plate reaching the electrode Q. Now the light is common incident. The frequency is h nu, right? This is frequency. Now, first rule says the photoelectric current. I again keep it very carefully. Photoelectric current. What do you mean by photoelectric current? The number of electrons. The number of electrons which are coming out. That depends on intensity. Again, the photoelectric current depends on the intensity of light. Now, what does it mean? For example, I have 40 watts lamp and I have 100 watts lamp. Now, you know very well that the 100 watts lamp is more intense light. That means it is having more amplitude. Then the number of electrons coming will be more. The number of electrons coming will be more. That can be studied with the help of a ammeter. Current will increase, but nothing else will happen. Yes, and this is the first law. But according to wave theory, the classical wave theory, what that says actually, more the intensity, more the energy of the electrons. What that says? That if the intensity increases, then the energy, kinetic energy of the electrons will be more. But we are going to prove that it is not true. The wave picture which says that intensity and kinetic energy are related is not true, and that is being decided by Einstein's photoelectric equation. I hope you understand the first part of it, that the intensity is dependent, that is electric current is dependent on the intensity. Now, why is it not dependent? That is the kinetic energy. Why is it not dependent on intensity? This is the question which we are going to now check it. See, what is the formula I have got here? That is H nu is equal to kinetic energy maximum. This is the first point. Yes, and W naught, anyway it has to come. Okay, this depends a constant depending on the nature of the material, which means that H nu is more or less proportional to kinetic energy maximum, and H is a constant. That means frequency is proportional to kinetic energy maximum. So the second law says the kinetic energy maximum depends on frequency and not intensity. Second law says the kinetic energy depends on the frequency. What do you mean by frequency? The number of waves coming per second. It depends on that, not on the amplitude. Whether it is higher amplitude or lower amplitude, that does not make any difference to the kinetic energy of the electron. Yes, intensity will affect the number of electrons. Maybe we can produce more electrons may come out, may be ejected out. But the kinetic energy, maybe if it is having 10 joule, they all will have only 10 joule. If I want to increase the energy of the electron, then I have to change the frequency, and this is very important. The second rule, the second law, it says that kinetic energy maximum of the photoelectron is directly proportional to the frequency and not the intensity. Yes, I hope you understand the second point, right? That is intensity and frequency. Now let us come to the third point. What is the third point? Third point is very simple, that for every emitter there is a minimum frequency, and that frequency is called threshold frequency. Again come here, H nu is equal to kinetic energy maximum plus, what is work function? Work function is minimum energy, that is H nu naught, where nu naught is called threshold frequency. Threshold frequency, that is the minimum frequency required for the emitter to give out the electron. So let me rearrange it now. H of nu minus nu naught is equal to kinetic energy maximum, or also I can say kinetic energy maximum is equal to h of nu minus nu naught. We also can write that instead of kinetic energy, we can take potential energy. EV naught is equal to h of nu minus nu naught. You see, this is the very important point. Nu minus nu naught. What is nu? Nu is the energy frequency of the incident photon, and nu naught is the threshold frequency of the metal. So nu should be greater than nu naught for photoelectric emission to take place. Nu has to be greater than nu naught for photoelectric emission to take place. So if nu is less than nu naught, there is no question of photoelectric emission taking place. You understand this point? Yeah. So the third point is that for every emitter there is a minimum frequency, and that frequency below which photoelectrons will not be emitted, and that is called threshold frequency. Now I come to the next point. Very simple, right? The classical wave theory says that when you have a metal, right, it is made up of electrons, we know. I am taking only surface electrons. What the wave theory says, when light is common incident, h nu, the incident light and the ejection of the electron, that is very sorry, the ejection of the electron, there is a small time gap. Yes, the light has to come, its energy, it has to give it to the electron, and it has to take the electron out, and it has to come out, and this is the wave picture. But the photoelectric emission based on Einstein's photoelectric equation says that there is no time lag. There is no time lag. There is no lagging of time. Okay, what does it mean? That means there is no, the process is instantaneous. The process of photoelectric emission is instantaneous. What does it mean? That means there is no time lag between incident photon and the ejected electron. There is no time lag. The moment it instant, the electron is coming out. The moment it hits it, it comes out. There is no time lag, and the time gap is around nanosecond, 10 power minus 9 second. That means it is nothing. Yeah. The moment it is incident, the photoelectrons are ejected. So this is also something we get it from the quantum theory. Only quantum theory can explain the photoelectric emission. That's why corpuscular theory, we talk about Newton, we saw only that it is corpuscles, particle, that could explain only reflection and refraction. When it came to interference and diffraction and polarization, Huygens principle, and we have wave theory. But when it came in 1900 to photoelectric emission, again corpuscular theory and wave theory cannot explain, and that's why we have quantum theory, and quantum theory is able to explain this, right? And this is one of the big achievement of quantum theory as such as a whole, and Albert Einstein, who got his Nobel Prize for his work on photoelectric emission. It's very simple, but great minds think of simple things. Great minds think of simple things and come out with great ideas, great explanations, right? It didn't strike anybody before Einstein. So Einstein ought to be a genius to think of this kind of equation, a simple one. In this video, last, I am going to discuss on two important graphs, and let us see how these graphs are and how well we understand. One is, it is between intensity. Both the graphs are based on intensity versus the plate potential. We call it plate potential, right? Now, how is this? Let us take one y-axis, right? Let me draw it straight little. Okay, let me take a y-axis and let me take x-axis. Let this be origin and this stands for plate potential. Okay, electrodes are there, so we are taking the plate potential. This is the positive x-axis and this is the negative x-axis, and here we are going to have stopping potential. What is stopping potential? Stopping potential is the negative potential. It is the negative potential which stops the photoelectron reaching the plate, reaching the electrode. Yeah, it is depends on the emitter. It also depends on the emitter. And in the x-axis, I am going to take intensity. Intensity. You know, intensity is directly proportional to current, photoelectric current. So both of them, they represent the same thing here. What is going to happen in the photo tube which you have taken? Again, I go back to the same photo tube, because without photo tube experimentally we cannot explain any of the concept. Okay, it was done by scientist by name Leonard, right? Leonard. Okay, so again, negative, positive, negative, positive. Yes, put a key here and put an ammeter here and then close the circuit. And this is Q and this is P and this is a window and the light is falling. Energy is H nu, right? Now look here. This plate is made up of zinc or anything you take. It will have a particular work function, particular threshold frequency, particular stopping potential. Okay, now let me take the stopping potential here is the negative V naught. What I am going to say? Negative V naught. Now, when I make this Q, okay, first this is negative, right? And it is electron is coming, electron is also negative, right? Negative, negative will repel. So, I am going to make the plate positive. When I make it positive, 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 come to zero potential and I go to positive values. Yes, less negative and zero and more positive. You will find that slowly the current will go on increasing, 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 and it will come to a point, and then after that the plate potential will not make much difference and it will have a saturated value, right? And this is for an intensity I. Okay, the intensity of the light which is coming and falling, and it on that you will find that first slowly, 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 slowly the electrons, as you decrease the negative potential, more electrons will go, and when it becomes positive, electrons are negative and the electrons will come. But electrons cannot it cannot increase. Why? The number of electrons emitted depends on the electrode here. This doesn't do any work at all. It can only absorb it can only collect the electron. But who is going to produce? Who is going to eject the electron? The ejection of electrons is done by the potential, the plate P. And how is that going to produce? That is because of the incident light. So, you will find that the current cannot increase like that. The current after a particular point, it can only have the collecting power and it will become something flat like this. I hope you get my point. Yeah. So, this is intensity when intensity is constant. For a particular metal, I have drawn this graph. This graph represents for only particular metal. Okay. Now, what is going to happen? I am going to increase the intensity. Let us say this intensity is I1, 40 watts. Now, what I am going to do? This is 40 watts, let us say. Now, I am going to come to another intensity, 100 watts. What did we learn in the first law? The intensity is proportional to the photoelectric current, or the photoelectric current is proportional to intensity. So the more the intensity, more the electron, and you will find that for the same metal, okay, let me just erase this and make it a little bit enlarge it, maybe extend it some more towards this direction. Yeah, positive x-axis, yes, and this is as usual intensity only, which is proportional to current. Okay, there is no change in any of these factors, right? Now more the intensity, the V naught stopping potential is same, the threshold frequency is same, the work function of the particular metal we have taken is same, all are same. So it will start from here, and you will find that it also will go on increasing, and at a particular point it will increase more, and it will reach a particular point, and more electrons will come out. That means the current will increase. Yes, of course, if you want, yes, for the difference's sake, what you can do is you can little bit change it like this, and you'll feel much better from this, right? That means the more the current is coming, that means the potential is go on increasing, the more the electrons are collected by Q, and then more the current is there. So you can better draw the graph something like this. It's also okay, or in some books they will give little converge it and take it, increase it somewhere. Both of them are one and the same, it does not matter. So this is photoelectric current or intensity with the plate potential. This is what I have done. Now we will do a last one more graph. In this graph, everything is remaining same. I am not changing anything, right? I am not changing anything, right? This is intensity is proportional to current, stopping potential, all these factors are there. I hope you can see little bit. I am going in the left hand side. This is minus negative. If you want, I can change a little bit for you, right? Minus V naught. Let us see. Now what is this case? I am going to allow the same intensity. Intensity of the light is going to remain constant, but I am going to change the plate. First I am going to say sodium plate I am taking, then I will take zinc plate. Sodium will have different work function, and it will have different threshold frequency, and it will have different stopping potential, and so let us say we call it as 1, and here zinc will have different work function, second metal, different threshold frequency and different stopping potential. Now first I take one plate and do the experiment with intensity. Let us say I am taking 40 watts bulb intensity, and you will find that as I change that, make it less negative and make it more positive, and you will find that it will come, and it will come to saturation value. Here the intensity of the light is same, I. Now I replace the plate P with the second metal. So I will put here, this is stopping potential of the first metal. Now stopping potential of the second metal is different. So I start here minus V naught of the second metal, but intensity is same 100 watts. So as it becomes less negative, it will go, and then somewhere again intensity is same, the current is same, only stopping potential is different, and you will find that two different metals, two different stopping potentials, and intensity is same. And this graph represents for the same intensity, if two different metals are exposed, how does the photoelectric current, or how it will be changing, or photoelectric emission will take place, right? I hope you got a clear picture of the photoelectric emission. This is the end of the photoelectric effect, emission, all the things we have covered. And next will be de Broglie's wave equation, and we will study about dual nature, how the electronic nature and this electron behaving as a matter, as a wave, this we will be studying based on de Broglie's wave equation, and the proof we will be studying with Geiger and Maston's. We have a Germer experiment, you know, that experiment we will be studying Davison and Germer. Yeah, I got confused a bit. Yeah, we will be studying about Davison and Germer's experiment. Based on that, this experiment is not in your syllabus, only a small inference, what we get it from here, that is Davison and Germer's experiment we will study in the next video. Thank you so much.